All right, the next discussion for this chapter has to do with something else new that we call formal charges. Sounds like something legal. Formal charges, how we describe things that are going on in Lewis structures, but we use them to decide which is a best Lewis structure when there's more than one possible way that something might be put together. Well, what in the world is formal charge? Formal charge for each atom in a structure is the difference in electrical charge between the number of valence electrons in an isolated atom and the number of electrons assigned to that atom in a Lewis structure. Remembering that we start with bare atoms and assign them in a structure as we work through the steps of a Lewis electron dot structure. So the goal of these things is to use them to predict and explain preferred and better choices of Lewis structures for a compound and for the atoms in a molecule or an ion. The sum of the formal charges of those atoms in a molecule or an ion has to equal the charge on that molecule or ion, and we'll use these to decide which Lewis structure is best for a particular compound. So let's look at that example with ozone that we used in talking about resonance. We look at calculating the formal charge on each oxygen atom in O3 ozone. And I'll write the name in here just because it's fun to know what ozone is. You've heard about it in the atmosphere. And it's nice to have a connection to something specific. So how do we figure that out? The formal charge on the oxygen atom is its number of valence electrons minus half of the bonding electrons. So the bonding electrons for the left oxygen are a double bond, 4 electrons. So half of the 4 is going to be 2. So 6 minus 2. And then subtract from that the number of non-bonding electrons, which is another 4. So 6 minus 4 is 0. The central oxygen atom is similarly has a formal charge calculated as follows. If you look at, there's 6 valence electrons every time for oxygen, all of these examples. That's what that is. And half of the bonding electrons, so there's 3 bonds for 6 total electrons. Half of those is 6 minus 3. And then we'll take away from that 2 more that are the non-bonding electrons. The non-bonding electrons are right here. And so 3 minus 2, both subtracted from 6, you end up with plus 1. And the third oxygen, you can calculate formal charges. Similarly, we start again with 6 valence electrons, because oxygen always has 6. And half of the bonding electrons, this time there's only 1 bond. And so it's half of the 2, so 6 minus 1. Minus what else? Well, it's the lone pair electrons. The lone pair electrons are 6 in this case, and the ending result is a formal charge of minus 1. So the formal charges on the oxygen in this molecule are 3 different ones. There's a 0 on the left, there's a plus 1 in the middle, and there's a minus 1 on the right. So what do you make of it? It's not going to make any difference right now because there's not an alternate structure that we can challenge here except for the fact that there's resonance. And the resonance form will have exactly the same combinations of 0, 1, and minus 1. It's a question of which end is shown with a double bond or not. So when we think about formal charges, we use funny cartoons if they help us. We think about splitting the bond in half, and we're thinking about the electrons half being assigned to each atoms in the bond. Whether it's a single, double, or triple bond, we split those electrons between the 2 atoms in that bond. So if we're going to make use of formal charges, here's an application of how we can make sense of it. Formaldehyde is a funny compound with CH2O, and if you don't know what you're going to do with it, you might imagine that carbon is in between things, which doesn't seem outrageous, or the oxygen in between things. Or you could put carbon in the middle and oxygen not between an oxygen or between hydrogen and carbon. How do we know which structure is going to be most reasonable? We use formal charges here. So the formal charges, again, are the electrical charge differences between the number of valence electrons for an isolated atom and the number of electrons assigned to it in a particular Lewis structure. So the formal charge, again, we look for the number of valence electrons in the free atom. We take away from that the total number of non-bonding electrons, and then again half of the bonding electrons. You do these in either order. You subtract both portions from the valence electrons of the free atom. The goal then at the end is that the sum of the formal charges of the atoms in a molecular ion has to be equal to the charge on the molecular ion if we've done it correctly. So here's our first hypothetical choice. We have to rationalize and make sense of what is going to be correct. In this case, we're putting together the total number of valence electrons in the diagram is going to be based on carbon having 4 electrons, 1 oxygen having 6 electrons. These are all the valence electrons again. And 2 hydrogens are going to provide, well, surprise, 2 electrons total. And that makes, if you add that all up, adds up to 12. In this particular diagram, it looks valid in the sense that each carbon and oxygen in those central positions has an octet. The hydrogens have 1 bond. That seems reasonable. And so the total number of electrons shown here is reasonable. We've got 12 electrons, and octets seem to be in place. Well, keep going. We need to think about the formal charges on each of the atoms in the structure. Now, both of the hydrogens are quite simple. We're not going to have to think very hard because they just have 1 bond, and we won't worry about them because they're not going to be the issue. So thinking about splitting the bonding electrons between the 2 atoms that are in the bond, let's do the formal charge on carbon, and then we'll do oxygen second to decide how the formal charges work. So for carbon, its total number of valence electrons that it always has is going to be 4. And so we start there, and we subtract from it the number of non-bonding electrons here, which is 2. And we will note that those are shown on top in this diagram. And then subtract from that half of the bonding electrons around the carbon. Well, the bonding electrons around carbon are 6 because there's 3 bonds. And half of 6 is 3. If you can do the math, it's a formal charge of -1. So there's those 3 bonds, and half of each of them are assigned to the carbon in that sense for calculating a formal charge. All right, formal charge of carbon done. Formal charge on oxygen is next. So the formal charge on oxygen is going to be based on its initial 6 electrons that it always has as its valence electrons. Subtract from the oxygen, what next? The total number of non-bonding electrons. Again, we have just 2 non-bonding electrons in this diagram. And half of its bonding electrons, which, there you go, there's the non-bonding electrons circled on the oxygen. And half of the 3 bonds, the half of the 6 electrons in bonds, are being assigned to the oxygen. And you subtract that 3 from the 2 and the 2 from the 6, and you end up with +1. So in this diagram with the 3 bonds around oxygen, you get a formal charge of +1 on the oxygen. Well, let's compare that then to the other possible structure that was proposed. The other possible structure shows 2 bonds between carbon and oxygen and 2 lone pairs on oxygen and none on the carbon. Again, the total number of valence electrons is still 12, which is where it better be. And total valence electrons is always where you want to start. Make sure you don't have the wrong number of electrons represented in your diagram. And even with this arrangement, we still have 2 single bonds, 1 double bond, and 2 lone pairs to add up to a total of 12 electrons. Let's do the formal charges and see how they come out any different. So for the carbon, what will we start with? Well, we start with the 4 valence electrons, right? And then we subtract from it all of its non-bonding electrons, which is none in this diagram, and half of the bonding electrons around it. Well, there's 4 bonds, and they're divided. 4 bonds is 2 electrons each. Divide them between carbon and its neighbors in each bond, and half of those is going to be 4. So 4 minus 4 is 0. Fair enough. There's your 4 bonds. The formal charge is 0. Now let's do the formal charge on oxygen. Again, we'll start off with the 6 valence electrons that it is found in a neutral free atom, and then subtract from the oxygen the non-bonding electrons. So the non-bonding electrons, there are 4 of them, 2 pairs, and they are noted in the diagram circled now. And then you subtract from that even more, so we're down to 2 so far, half of the bonding electrons. So how many bonding electrons do we have there? There's 4 because it's 2 bonds. It's a double bond, and so half of those is another 2, and the formal charge ends up to be a total of 0. So half of those 2 there. So the charges the formal charges on carbon and oxygen are 0 and 0 in this particular arrangement for formaldehyde. Well, what do we make of that? Well, it turns out that this is the preferred structure for formaldehyde, where you put a double bond between carbon and oxygen. Why? Because, well, let's first of all verify. For a neutral molecule, the Lewis structure is preferable when there are no formal charges. In other words, 0 and 0 is good, so that one is preferred in the second choice that we just worked our way through. Lewis structures with large formal charges are less plausible than those with small formal charges. Again, 0 is less than 1 that we had in the previous example. So we would prefer small formal charges. And we'll select those as better choices. And among Lewis structures having similar distributions of formal charges, the most plausible one is the one which has the negative formal charges placed on more electronegative atoms. In other words, things in that top right corner of the periodic table. So which is the most likely structure for the formaldehyde? One where you have a -1 and a +1 on the carbon and the oxygen, or the one where you have a 0 and a 0 for the carbon and the oxygen. In this case, this fits with no formal charges on either of those atoms where we need to put formal charges. Hydrogen is going to be 0 in either of these examples. All right, let's try another one. So let's do the formal charges for the nitrite ion NO2-, and you'll have to look it up from somewhere in your notes, and we're looking to make sure that the sum of the formal charges in the molecular ion has to equal the charge on the molecular ion. So I'm going to pull together the nitrite ion's Lewis structure because I've worked it out ahead of time to save us some writing on the screen. So we'll have 2 oxygens. One has a double bond, one has a single bond, and the whole thing has a minus charge because there's enough electrons in addition to the electrons from the 2 oxygens and a nitrogen to give an overall negative charge. All right, so now in order to do this, we have to come up with formal charges on each of the atoms in this structure. We're not choosing between structures. This one turns out to have resonance structures, yes. So let's do the left oxygen first. So the total number of valence electrons for any oxygen is always 6. Subtract from that the number of non-bonding electrons, which is 6. True enough. And then half of the bonding electrons between oxygen and nitrogen, so 1/2 of 2 is another 1. So the formal charge on that atom is -1. Write it here. So the center oxygen, sorry, it's the center nitrogen, hello. Nitrogen has what kind of formal charge? So 5 is its total number of valence electrons in the free atom. It has no lone pairs or non-bonding electrons in this diagram, and it will be assigned 1/2 of the 6 in the 3 bonds around the nitrogen as electrons assigned to it. And so if you can do the math, we're going to have a charge, 1/2 of 3, all right, whoops. Oh, I forgot something in the diagram. Hello, no wonder we were not correct. There was a lone pair necessary there. No correct assertions without the correct diagram. Have to have that. So fix your answers here. So there were, in fact, some lone pair electrons here. 2. And so 5 minus 2 minus 1/2 of 6 is 3. We end up with a 0. Wow, sorry about that. I was not paying attention to my diagram carefully. The right oxygen, let's come up with the formal charges there. I didn't write the charge under the nitrogen. The right oxygen, all right, 6 valence electrons. As usual, the number of non-bonding electrons on the oxygen, we're going to subtract there, are 4. And then 1/2 of the 4 electrons in a bond, so 1/2 of 4 ends up to be 2, right? So 6 minus 4 minus 2 is 0. So the formal charge on the last oxygen in this structure is also 0. So as Lewis structures go, those all add up to the charge of -1, which is supposed to be correct. And the formal charges make sense. They're as small as you're going to get for something with a charge of -1. Lewis structures with formal charges do take practice. Notice that having your lone pairs in the right places is key and essential to getting them correct. Be very careful as you work your way through these. I hope this helps. Good luck on your assignments. See you in class.